Hello everyone, and welcome to my channel. This channel is for educational purposes. And on this channel we take a look at different great theories of everything, all-encompassing theories, things that you can, build your paradigm around, help you with your holistic worldview and your awakening to 5D consciousness. Today is our 487th video on the reciprocal system of theory from Dewey B. Larson. And if you'd like to get a more thorough rundown about the reciprocal system before you watch this video, you can go and watch any of my first 474 videos that I did on this topic, where I go into a little bit of depth about the reciprocal system. But today we're just going to start right up, kind of assuming that you understand a little bit about the reciprocal system, because otherwise I don't really get too much of the reading done. We're reading directly from one of Larson's books. Today we're reading from his 1987 book, Basic Properties of Matter. Basically what Larson did is in 1959 he proposed his two fundamental postulates about how the universe operated. Then through a process of deduction he elaborated his postulates into a theoretical universe, what his universe would look like if his postulates were correct. And then he compares his theoretical universe with the measured universe of the so-called scientists, legacy scientists out there, and that they have put together in their laboratory experiments and compiled in their scientific tables. And he does that with the field of chemistry, with the book Basic Properties of Matter. We're in chapter 12 now on scalar motion, which is a fundamental. Larson is one of the few scientists to propose a universe based on motion, a universe made out of motion, not matter, not energy, but motion. And in particular, when Larson refers to motion, he's referring to scalar motion. That is the substance of the universe, the source of everything else. And so in this chapter, chapter 12, he goes over, the qualities and the evidence of the scalar motion. We started this chapter yesterday, and so you might want to go back and watch the first part of this. But we'll get into the second part here momentarily. So I think maybe we have summed it up enough. Just if you want to get into kind of the more of the ins and outs of the reciprocal system, just watch one of those first 474 videos. I'll just say here first of all that we're looking here at Larson's book on chemistry, but Larson's is a general theory. It plugs into every subject. So if you understand how it operates in the field of chemistry, that gives you a leg up on understanding how it operates in astronomy or in economics or in metaphysics. He attempts to apply his theory to all subjects. And he ran out of time because he died at the age of 92 in 1990. And so maybe he wasn't able to apply it to every subject, but some of his followers have applied it into further fields: meteorology, geology, crypto history, and we'll see what other people come up with. But Larson's theory is a generalized theory. So, just what the fact that we're talking about chemistry, don't think, oh, well, I don't really care about chemistry. No, think about it in terms of analogies, and that, okay, this is kind of a baseline about how you work with the reciprocal system, which gives me guidelines to how I can use it in whatever subject I want to apply it to. Okay, it's taking over here in chapter 12, about halfway through. The present day field, like an electric field or a gravitational field or a magnetic field, the present day field is just as intangible as in Einstein's space. There is no physical evidence of its existence. All that we know is that if a test object of an appropriate type is placed within a certain region, it experiences a force whose magnitude can be correlated with the distance to the location of the originating object. What existed before the test object was introduced is wholly speculative. Faraday's hypothesis was that the field is a condition of stress in the ether. Present-day physicists have transferred the stress to space in order to be able to discard the ether, a change that has little identifiable meaning. As R.H. Dick puts it, quote, "One suspects that with empty space having so many properties, all that had been accomplished in destroying the ether was a semantic trick. The ether had been renamed the vacuum." End quote. P.W. Bridgman, who reviewed this situation in considerable detail, arrived at a similar conclusion. The results of analysis, he says, quote, "suggest that the role played by the field concept is that of an intellectual dummy, which cancels out of the final result." The theory of the universe of motion gives us a totally different view of this situation. In this universe, the reality is motion. Space and time have a real existence only where, and to the extent, space and time have a real existence only where, and to the extent that, they actually exist as components of motion. On this basis, extension space, the space that is represented by the conventional reference system, is no more than a frame of reference for the spatial magnitudes and directions of the entity, motion, that actually exists. It follows that extension space cannot have any physical properties. It cannot be curved or modified in any other way by physical means. Of course, the reference system, being nothing but a human contrivance, could be altered conceptually, but such a change would have no physical significance. The status of extension space as a purely mental concept devised for reference purposes rather than a physical entity likewise means that this space is not a container or background for the physical activity of the universe as assumed by conventional science. In that conventional view, everything physically real is contained within the space and time of the spatio-temporal reference system. When it becomes necessary to postulate something outside these limits in order to meet the demands of theory construction, it is assumed that such phenomena are, in some way, unreal. As Werner Heisenberg puts it, they do not exist objectively in the same sense as stones or trees exist, end quote. The development of the theory of the universe of motion now shows that the conventional spatio-temporal system of reference does not contain everything that is physically real. On the contrary, it is an incomplete system that is not capable of representing the full range of motions which exist in the physical universe. It cannot represent motion in more than one scalar dimension. It cannot represent a scalar system in which all elements are moving. nor can it correctly represent the position of an individual object that is moving in all directions simultaneously. That is, an object whose motion is scalar and therefore has no specific direction. Many of the other shortcomings of this reference system will not become apparent until we examine the effects of very high speed motion in volume 3. But that's his book on astronomy, universe of motion. But those that have been mentioned have a significant impact on the phenomena that we are now examining. The inability to represent more than one dimension of scalar motion is a particularly serious deficiency, inasmuch as the postulated three-dimensionality of the universe of motion necessarily permits the existence of 3 dimensions of motion. Only one dimension of vectorial motion is possible, because all 3 dimensions of space are required in order to represent the directions of this one-dimensional motion. But scalar motion has magnitude only, and a 3-dimensional universe can accommodate scalar motion in all 3 of its dimensions. Since the conventional reference system cannot represent all of the distributed scalar motions, and present-day science does not recognize the existence of any motions that cannot be represented in that system, it has been necessary for the theorists to make some arbitrary assumptions as a means of compensating for the distortion of the physical picture due to this deficiency of the reference system. One of the principal steps taken in this direction is the introduction of the concept of fundamental forces, autonomous entities that exist in their own right and not as properties of something more basic. The present tendency is to regard these so-called fundamental forces as the sources of all physical activity, and the currently popular goal of the theoretical physicists, the formulation of a grand unified theory, is limited to finding a common denominator of these forces. Gravitation is, in a way, an exception, as the currently popular hypothesis as to the nature of the gravitational force. As gravitation is, in a way, an exception, as the currently popular hypothesis as to the nature of the gravitational force, Einstein's general theory of relativity does attempt an explanation of its origin. According to this theory, the gravitational force is due to a distortion of space resulting from the presence of matter. So far as can be determined from the scientific literature, no one has the slightest idea as to how such a distortion of space could be accomplished. Arthur Eddington expressed the casual attitude of the scientific community toward this issue in the following statement, quote, "We do not ask how mass gets a grip on space-time and causes the curvature which our theory postulates," end quote. But unless the question is asked, the answer is not forthcoming. In Newton's theory, the gravitational force originates from mass in a totally unexplained manner. In Einstein's theory, it is a result of a distortion or a curvature of space that is produced by mass in a totally unexplained manner. Thus, whatever its other merits may be, the current theory, general relativity, accomplishes no more toward accounting for the origin of the gravitational force than its predecessor. In order to arrive at such an explanation, we need to recognize that force is not an autonomous entity. It is a property of motion. The motion of an individual mass unit is measured in terms of speed or velocity. The total amount of motion in a material aggregate is then the product of the speed and the number of mass units, a quantity formerly called quantity of motion, but now known as momentum. The rate of change of the motion of the individual unit is acceleration. That of the total quantity of motion is force. The force is thus the total quantity of acceleration. The significance of this in the present connection is that force not only produces an acceleration when applied to a mass, a fact that is currently recognized, it is an acceleration prior to that application, a fact that is currently overlooked or disregarded. In other words, the acceleration is simply transferred. For example, when a rocket is fired, the total quantity of acceleration available for application to the rocket, the force, is the sum of the quantities of acceleration of the individual particles of the gas produced from the propellant. The division of this total quantity among the mass units of the rocket determines the acceleration of each individual unit and therefore of the rocket as a whole. Since force is a property of motion rather than an autonomous entity, it follows that whenever there is a force, there must also be a motion of which the force is a property. This leads to the conclusion that a gravitational force field is a region of space in which gravitational motions exist. In the context of conventional physical thought, this conclusion is unacceptable, since there are no moving entities in an occupied field. The information about the nature of scalar motion developed in the earlier pages clarifies this situation. A material aggregate is moving gravitationally in all directions, but the conventional spatial reference system is unable to represent a system of motions of this nature in its true character. As previously indicated, where the scalar motion AB of object A, the massive object now under consideration, toward object B, the test mass, cannot be represented in the reference system because of the limitations of that system. This motion AB is shown as a motion BA, that is, a motion of the test mass B toward the massive object A, constituting an addition to the actual motion of that test mass. Because of the spherical distribution of the scalar motions of the atoms of mass A, the magnitude of the motion imputed to mass B depends on its distance from A and is inversely proportional to the square of that distance. Thus, each point in the region surrounding A corresponds to a specific fraction of the motion of A, representing the amount of motion that would be imputed to a unit mass if that mass is actually placed at this particular point. Here, then, is the explanation of the gravitational field, and by extension, all other fields of the same nature. The field is not something physically real in the space. Quote, for the modern physicist, as real as the chair on which he sits, end quote, as asserted by Einstein. Nor is it, as Faraday surmised, a stress in the ether. Neither is it some kind of change in the properties of space, as envisioned by present-day theorists. It is simply the pattern of the magnitudes of the motions of one mass that have to be imputed to other masses because of the inability of the reference system to represent scalar motion as it actually exists. No doubt this assertion that what appears to be a motion of one object is actually, in large part, a motion of a different object is somewhat confusing to those who are accustomed to conventional ideas about motion. But once it is realized that scalar motion exists, and because it has no inherent direction, it may be distributed over all directions, it is evident that the reference system cannot represent this motion in its true character. In the preceding analysis, we have determined just how the reference system does represent this motion that it cannot represent correctly. This may appear to be a return to the action at a distance that is so distasteful to most scientists, but in fact, the apparent motion on distant objects is an illusion created by the introduction of the concept of autonomous forces to compensate for the shortcomings of the reference system. If the reference system were capable of representing all of the scalar motions in their true character, there would be no problem. Each mass would then be seen to be pursuing its own course, moving inward in space, independently of other objects. In this case, accepted scientific theory has gone wrong because prejudice supported by abstract theory has been allowed to override the results of physical observations. The observers keep calling attention to the absence of evidence of the finite propagation time that current theory ascribes to the gravitational effect, as in this extract from a news report of a conference at which the subject was discussed. Quote, "When it, the distance, is astronomical, the difficulty arises that the intermediaries need a measurable time to cross, while the forces in fact seem to appear instantaneously." End quote. But it is assumed that we must accept either a finite propagation time or action at a distance, which, as Bridgman once said, quote, "is a concept to which many physicists have a violent allergy." Einstein's theory, which supports the propagation hypothesis, has therefore been accorded a status superior to the observations. The following statement from a physicist brings this point out explicitly. Quote, Nowadays we are also convinced that gravitation progresses with the speed of light. This conviction, however, does not stem from a new experiment or a new observation. It is a result solely of the theory of relativity. End quote. This is another example of a practice that has been the subject of critical comment, in several different connections in the preceding pages of this and the earlier volume. Overconfidence in the existing body of scientific knowledge has led the investigators to assume that all alternatives in a given situation have been considered. It is then concluded that an obviously flawed hypothesis must be accepted in spite of its shortcomings because there is no other way. Time and again, in the earlier pages, development of the theory of the universe of motion has shown that there is another way. one that is free from objectionable features. So it is in this case. It is not necessary either to contradict observation by assuming a finite speed of propagation or to accept action at a distance. Some of the most significant consequences of the existence of scalar motion are related to its dimensions. This term is used in several different senses, two of which are utilized extensively in this work. When physical quantities are resolved into component quantities of a fundamental nature, these component quantities are called dimensions. Identification of the dimensions in this sense of the basic physical quantities has been an important feature of the development of theory in the preceding pages. In a different sense of the term, it is generally recognized that space is three-dimensional. Conventional physics recognizes motion in three-dimensional space and represents motions of this nature by lines in a three-dimensional spatial coordinate system. But these motions which exist in three dimensions of space are only one-dimensional motions. Each individual motion of this kind can be characterized by a vector, and the resultant of any number of these vectors is a one-dimensional motion defined by the vector sum. All three dimensions of the spatial reference system are required for the representation of one-dimensional motion, and there is no way by which this system can indicate a change of position in any other dimension. However, the postulate that the universe of motion is three-dimensional carries with it the existence of three dimensions of motion. Thus, there are two dimensions of motion in the physical universe that cannot be represented in the conventional spatial reference system. In common usage, the word dimension is taken to mean spatial dimensions, and reference to these dimensions is ordinarily interpreted geometrically. It should be realized, however, that the geometric pattern is merely a graphical representation of the relevant physical magnitudes and directions. From the mathematical standpoint, an n-dimensional quantity is one that requires n independent magnitudes for a complete definition. Thus, a scalar motion in three dimensions, the maximum in a three-dimensional universe, is defined in terms of three independent magnitudes. One of these magnitudes, that is, the magnitude of one of the dimensions of scalar motion, can be further divided dimensionally by the introduction of directions relative to a spatial reference system. This expedient resolves the one-dimensional scalar magnitude into three orthogonally related submagnitudes, which together with the directions constitute vectors, but no more than one of the three scalar magnitudes that define a three-dimensional scalar motion can be subdivided vectorially in this manner. Here is a place where recognition of the existence of scalar motion changes the physical picture radically. As long as motion is viewed entirely in vectorial terms, that is, as a change of position relative to the spatial reference system, there can be no motion other than that represented in that system. But since scalar motion has magnitude only, there can be motion of this character in all three of the existing dimensions of the physical universe. It should be emphasized that these dimensions of scalar motion are mathematical dimensions. They can be represented geometrically only in part because of the limitations of the geometrical representation. In order to distinguish these mathematical dimensions of motion from the geometric dimensions of space, in which one dimension of the motion takes place, we are using the term scalar dimension in a manner analogous to the use of the term scalar direction in the earlier pages of this and the preceding volume. Okay, that seems a little abrupt, but that is the end of the chapter, chapter 12 on scalar motion. And if you really want to learn the reciprocal system, I'd say that that is a crucial chapter to ground your understanding in. That is, Larson is, when he talks about a universe of motion, he is talking about a scalar motion, a motion that has a magnitude that has no direction, no specific direction. Just like if you took a balloon and you put dots on it, you blow up the balloon, all the dots are moving away from one another, but they're not moving in any specific direction. Every dot is moving away from every other dot. And so too, if you suck in the balloon and contract it, they will all be moving toward each other. That outward motion of the balloon is what Larson calls the progression, and the inward motion of the balloon is analogous to gravitation. And manifestation in the universe is to take that source, that empty universe, the omnipresent and eternal force of the progression that is always there at all times and all places, and roll it back, roll back that outward motion, harness it, roll it back until it becomes gravitation, which is matter. Okay, and then which can become aggregates of matter and planets and galaxies and so on. So that is, the fundamental thing that you gotta get started with the reciprocal system. You start with the scalar motion. It's the progression, calls it the progression of the natural reference system, the natural reference system, implying that this goes beyond the spatial reference system and beyond a temporal reference system. And you roll that back to manifest. So, and then the other key thing to keep in mind with the reciprocal system is that motion is the relationship between space and time. Space and time have no other significance other than their relationship in motion, and that is a reciprocal relationship. Motion is a fraction with space or time as the numerator and time or space as the denominator. But they come in 1, 2, or 3 dimensions. All right.